All right, in this section we're going to be looking at trigonometric integrals. The primary technique is going to be use substitution. There might be a little bit of integration by parts, and then use of Pythagorean identities and a couple other trigonometric identities. So the goal is, if you have sines and cosines, you want to convert everything, for example, to sines, and then you just have one cosine left over, so u is sine, du is cosine, or you have everything converted into cosines, and you have one sine left over. U is cosine, du is minus sine. And so that's kind of the idea here with integrals involving sines and cosines. Now, the first one I have on here is the sine cubed in the integral. And so that one doesn't have any cosines, so we're going to have to get some cosines or some sines in there. All right, so let's go ahead and recall the Pythagorean identity. Sine squared plus cosine squared is equal to 1. If we solve this for sine squared, the sine squared of x is equal to 1 minus the cosine squared x. Okay, so we're going to rewrite the sine cubed as the sine squared times the sine of x dx. Rewriting the sine squared is 1 minus cosine squared x times the sine of x. All right, this is good to go. Okay, so we're ready to do our u substitution. U is cosine of x. Differential du is equal to negative sine x dx. So in order to get an exact match, we're going to go ahead and introduce two negatives so that they offset each other. Okay, so you have the negative in the front of the integral, which is going to offset the negative on the sine of x that we've introduced there. So we have a nice clean substitution. So it's going to be negative integral of 1 minus u squared, and then du. So it's going to be negative u plus u cubed over 3 plus the constant of integration. So it's going to be a negative cosine of x plus cosine cubed over 3 plus constant of integration. And then we can go ahead and verify that we have found the correct antiderivative by taking the derivative of the antiderivative. And so that's going to be sine plus cosine squared x times negative sine by the chain rule. So you can factor out a sine of x, and we have 1 minus cosine squared x, and 1 minus cosine squared x is sine squared, so we have sine times sine squared, and so we get sine cubed, which is the original integrand, so that looks good. That looks good. Alrighty, let's move on and look at another example. So what about the integral of sine cubed, cosine cubed dx? And this one you can actually do either way. We can either save a sine or a cosine and do use substitution where you use sine or cosine. We'll do this both ways. In your textbook and also the notes, there's some guidelines on how to do those. I don't really think of the guidelines, more of I just kind of look at how can I have just a sine or a cosine left over. So let's go ahead and write sine squared is equal to 1 minus cosine squared. So we're going to convert to cosines and save a sine. So this is the integral of sine times sine squared cosine cubed dx. And we're going to replace the sine squared with 1 minus cosine squared x, and then times the cosine cubed x dx. This is ready for u substitution. U is cosine. Differential du is equal to negative sine dx. Okay, so we need a negative sign, so we can introduce a negative sign, but to offset that, we'll put in a second negative, so they will offset. All right, so this becomes the integral of negative integral of 1 minus u squared times u cubed du. So we can put that negative back in, so that's going to give us u to the 5th minus u cubed du. So it's going to be u to the 6th over 6 minus u to the 4th over u plus c. Go ahead and make the replacement, so 1/6 cosine to the 6th x minus 1/4 cosine to the 4th x plus constant of integration. And then, of course, we can always verify that this is, in fact, the correct antiderivative by taking the derivative. So that is going to give us cosine to the fifth x times negative sine of x by the chain rule, minus cosine cubed times negative sine x by the chain rule. Greatest common factor here is a negative cosine cubed sine of x. And when we factor that out, we have a cosine squared x minus 1. 1 minus cosine squared is sine squared. So let's go ahead and factor out a negative so that we'll have 1 minus cosine squared. We've got the double negatives will cancel, so we have cosine cubed x sine x, and then the 1 minus cosine squared is sine squared. And so we're back to the sine cubed cosine cubed, which was the original integrand. Okay, so we're going to go ahead and we're going to look at the exact same integral, but we're going to convert everything into sine. So u will be sine, and then du will be cosine dx. Okay, so we're going to do the other substitution. So sine cubed, cosine cubed. We're going to take the integral of that. So cosine squared x is equal to 1 minus sine squared x. We're going to use that to convert everything to sine. So rewrite the cosine as cosine squared cosine x. So that cosine cubed we rewrite as cosine squared times cosine. And then we're going to replace the cosine squared with 1 minus sine squared. Then we have a cosine left over, and then differential dx. U is equal to the sine. Differential du is equal to the cosine x dx. So this gives us the integral of u cubed times 1 minus u squared du. So it becomes the integral of negative u to the fifth plus u to the third du, which is going to be negative 1/6 u to the sixth plus 1/4 u to the fourth plus c. Go ahead and replace the u with the sine, so negative 1/6 sine to the sixth plus 1/4 sine to the fourth plus c. And then, of course, if you want to verify it, we could go ahead and take the derivative here. Okay, so that's going to be negative sine to the fifth x, cosine x by the chain rule, plus sine cubed x, and then cosine by the chain rule. We're going to factor out a sine cubed and a cosine x. And what we have left over is sine squared x plus 1, and that's going to be cosine squared. So we have sine cubed x, cosine x, and the negative sine squared plus 1 is cosine squared. And so there we are. We have sine cubed, cosine cubed, our original integrand there. Okay, and so the antiderivatives are going to look different between how we do the u substitution. They are equivalent. We'd have to use the Pythagorean identities to get them to look the same. To get from this one in terms of sines to the previous one in terms of cosines. Okay. All right, we're going to look at one more. So all of these were kind of the variety of where the sine or the cosine were odd. So when you have the sine or the cosine is odd, you want to convert everything to either sines or cosines, and then, so if you convert everything to sines, you want to save one more cosine to do your u substitution. If you convert everything to cosines, you want to save a sine for your u substitution. So what happens when both the exponents are even? So what about the integral of sine squared cosine squared dx? Well, from pre-calculus, you would have had power-reducing formulas. They come from the double angle formula. And the sine squared x is equal to 1 minus cosine 2x over 2. And then the cosine squared x is equal to 1 plus cosine of 2x over 2. So we don't have an antiderivative for sine squared or cosine squared. And the other problem is, I can't save a one sine or one cosine and do my u substitution because I need sine squared or cosine squared in the Pythagorean identity to make the replacement. So we have to have another technique here. And so power reducing is certainly helpful. So we're going to go ahead and do the power reduce. And sine squared is 1 minus cosine 2x over 2 times the cosine squared is 1 plus cosine 2x all over 2 differential dx. Okay, we're going to have a 1/4. We'll slide that out. And then it's a difference of squares. 1 minus cosine 2x times 1 plus cosine of 2x is going to be 1 minus cosine squared of 2x. Okay. And so we still have like a cosine squared. And if we were going to do a u substitution, u was cosine, du would be negative sine, but we don't have a sine. And so we're a little bit stuck. And so we're going to have to use the power reduced formula again. So this is going to be 1/4 integral of 1 minus, okay? Now, notice what happens to the angle here. It's a 1, and then it becomes a 2. It's a 1, and it becomes a 2. So a 2, an angle of 2, is going to become an angle of 4. It comes from a double angle formula. So minus cosine squared of 2x will become 1 plus cosine, and double that, so that'd be 4x all over 2 dx, okay? So it's going to be 1/4 integral of, and then we have 1 minus 1/2, which is 1/2, minus cosine 4x all over 2 dx. So it's going to be 1/4 times 1/2 x minus the sine of 4x over 4, and we already had an 2 underneath there also, plus c. So we're going to factor out an eighth. So 1/8 times 1/4 is 1/32. 1/2 divided by 1/8 is 4x, and then 1/8 divided by 1/8 is just 1, so we got the minus sign of 4x. And then plus c. So that is our antiderivative. Again, if we want to verify that it is the antiderivative, let's go ahead and take the derivative of that. So we're going to take the derivative of 1/32 times the quantity 4x minus sine of 4x, and then plus c. So it's going to be 1/32 times 4 minus 4 cosine of 4x. Then we're going to use a double angle formula here. So cosine of 2x, there are 3 formulas: cosine squared minus sine squared, or 2 cosine squared x minus 1, or 1 minus 2 sine squared x. So 1/8. So I went ahead and factored the 4 out. So 4/32 is 1/8. Okay, so 1/8, 1 minus, okay. And I'm going to go ahead and use the cosine of 2x is equal to 1 minus 2 sine squared. Now notice that this was a 2 and it turned into a 1, so a 4 will turn into a 2 when we use this formula. So this is going to be 1 minus 2 sine squared of 2x, okay? Okay, so that's going to be 1/8 times, let's see, the 1s will absorb, negatives will absorb, so it'll be 1/8 times the 2 sine squared of 2x, so it'll be 1/4 sine squared of 2x, okay? And so we actually have another double angle formula. So sine of 2x is equal to 2 sine x cosine x. So it's going to be 1/4, and then 2 sine x cosine x quantity squared. So then we'll have the 2 squared times the 1/4, so those will absorb, and then we'll certainly get our sine squared and our cosine squared. And so we do have the original integrand again there, okay? Alrighty. So in the next video, we're going to do kind of some special case integrals, 2 special case integrals, maybe 3 of them, and then we'll look at playing the same game with secants and tangents. So secants and tangents, you want to leave over a secant squared or secant x tangent x, because the derivative of tangent is secant squared, derivative of secant is secant x tangent x. And so it's going to be a very similar idea. You'll have different Pythagorean theorems, and then you're going to be wanting to leave, instead of a sine or a cosine, a secant squared or a secant tangent x. But the idea is very similar. All right, so we'll see you in the next video.